Hello everyone, today we're talking about computation and properties of AX, matrix times vector. And the idea here is we want an easier way, put that in quotes because it still will take some work, we want an easier way to compute the vector A times X. So A times X is matrix times vector, right? Now let me do this basically by an example, but let's recall the definition of AX in terms of linear combinations. That's how we define this thing. Okay, so let me do this with an example. So e.g. if A is, let's do 1, 2, minus 1, 0, 5, 3. Let's take x to be just a general x1, x2, x3. Then what is A times x? Then AX, right, by definition, this is, right, we take those columns of A, write down the columns of A, and then what I'm going to do is I'm going to make a linear combination where I take, the weights as the entries of the vector x. So those weights are given by the entries of x, and this is my definition of A times x. Let's actually work this out. Let's compute what it is. It's a vector, and the first entry is going to be what? x1 plus 2x2 minus x3, right? If I take the x1 times 1 plus 2 times x2 minus x3. The second entry is, 0 plus 5x2 plus 3x3. So this is the vector that I get by taking A times x. Okay, so let's kind of investigate this a bit further and see if there's any pattern, if there's any rule that we observe here. So let me note that the first entry of A times x, so this thing here, right, what is that? Notice that the way I got this entry is actually determined by the first row of A. So this is given by the sum of the, what do I do is I take every entry in that first row of A, and I take the corresponding product with entries of x, and then I add them all up. So it's the sum of the products of the entries in the first row of A and the vector x. That's maybe a mouthful here, but the point that I'm trying to get at is that the first entry of AX is given by information in the first row of A. So if I look at that first row, what I do is I take 1 times x1 plus 2 times x2 plus minus 1 times x3. So I took the first entry times x1, the second entry times x2, the third entry times x3, and I added them all up. And that's what I got here. Similarly, how did I get the next entry? The second entry of AX is, maybe I won't write it out, but it's the same deal. What I do now is if I'm looking at the second entry, let me make a box around that. This now is determined by the second row. So I take the second row, which is 0 times x1 plus 5 times x2 plus 3 times x3. And that's what I got here. This is 5x2 plus 3x3. And again, I got that entry, the second entry, by just taking the information from the second row. Okay? Let me write this out. Let me try to write this out in kind of a rule. So they call this the row vector rule for matrix times vector, I'll say. So what this is saying is that the ith entry of the matrix of the vector A times x is given by the sum of the products. So you're adding up a bunch of products, the sum of the products of the corresponding entries from row, if you're doing the ith entry, it's going to be the row I of A and from the vector x. Okay, it's called the row vector rule. So it's a little bit of a mouthful. Let me do this with another example, I guess. Let's take that same matrix 1, 2, minus 1, 1, and 0, 5, 3, and let me multiply it by, I don't know, let's actually do a particular choice of numbers here. If it's 4, 3, 7. So what is this going to equal? So we know now that this is a 2 by 3 matrix times a vector of length 3. This is going to be a vector with 2 entries. Okay? So the first entry, what I do is I take that first row and I do this thing where I take the corresponding products and add everything together. So this will be 1 times 4, right, 1, 4, plus 2 times 3, plus minus 1 times 7. Okay? All right, again, I'm taking the first row and I'm taking the first entry times the first, second entry times the second, third entry times the third. And what do I get is, what is this? 4 plus 6 minus 7, so that's 3. The second entry will be, well, I look at the second row of A, and I do the same thing. So this will be 0 times 4, plus 5 times 3, plus 3 times 7. Right, again, taking the corresponding entries, multiplying them together, and adding everything. So what is this? 0 plus 15 plus 21. What is that? 34. Okay, and so now those will be my 2 entries. So this actually equals, right, those numbers, 3 and 34. Sorry, 36, right? What is that? 15 plus 21 is 36. So this is 36. Okay, math is hard. Anyway, so that's the idea. That's the row vector rule for matrix multiplication. If you did the other kind of, the definition of matrix multiplication, you would get the same thing. So let me just point out that this is the same thing as taking 4 times that first column, plus 3 times the second column, plus 7 times the third column. If you check, you'll get that this is also equal. Okay, one other thing I want to point out is, well, just one more example maybe. What if you take a matrix that looks like this? So a 3 by 3 matrix that is square, right? It's a 3 by 3 and it has 1s down the diagonal and 0s everywhere else. If you multiply this by anything, let's say RST, what do you get here? Well, this is going to be another 3 by 1 vector. It's going to be a vector of length 3, dimension 3. And what's the first entry? So this first entry is going to be, you take that first row and do the thing. So it's going to be 1 times R plus 0 times S plus 0 times T, right? Second entry will be, I take the second row of this matrix and I take 0 times R plus 1 times S plus 0 times T. This is going to be, the last entry will be 0 times R plus 0 times S plus 1 times T. So what do I get here? I get just RST again. So that's kind of cool. I took a matrix times a vector and I got back the same vector. And in fact, this has a name, this matrix. This is called the identity matrix. And I would call this I3 here because it refers to the fact that it has 3 entries. In general, IN is an n by n matrix with 1s on the diagonal. So the diagonal, I mean the diagonal, from the upper left to the bottom right, they're all 1s. And then the other property is that it has 0s everywhere else. Okay? And this matrix always has this nice property that it eats a vector, multiplies by a vector, and spits out the same thing that you entered. Okay. Last thing I want to finish off with is just, I want to observe a few important properties of matrix multiplication. And I'll do this a little bit informally, but let me just say that there's 2 properties I want to focus on here. First of all, if I take A, A is my, let me say, this is of matrix times vector. So the first one says that if I take A times the sum of 2 vectors, right, this sum is a new vector, and it turns out that it's the sum of the products. Okay? And then the other property I want to emphasize is that if you take A times the scalar of a product, so the two things we can do with vectors, as you know, is you can add vectors or you can scale them. In the first case, if you add vectors and you apply matrix multiplication, it's actually just the sum of those two products. The other thing you can do with a vector is you can scale it. If you scale a vector and you multiply it by a matrix, it turns out it's just the scalar of the product of that matrix, right? And the way you would prove these things, well, you would go back to the definition of matrix multiplication. So let me just show you kind of how A works. So notice that let's let U be, say, U1 through UN. Let's take V to be V1 through Vn. Then what you get here is that when I take A times U plus V, what is that? Well, that's A times, I'm going to add those two vectors together. So if I add the vectors, I get U1 plus V1 as my first entry, U2 plus V2 down to UN plus Vn, right? That's now the vector that I'm going to multiply A by. And as you know now, when I take a matrix times a vector, right, by definition, this gives me, well, it's a linear combination. And what are the weights going to be? They're going to be the entries of that vector. So this is U1 plus V1 is my first weight. My second weight is the second entry of that vector, U2 plus V2. Dot, dot, dot. This last weight would be UN plus Vn. Okay. But we know now that if I take U1 plus V1, that's a number, and I scale it, if I scale A1 by that, that's the same as U1 A1. And I'm going to leave, and so this will now be plus V1 A1. And if I now kind of peel off all the U's that I see, this will be UN times AN. And then what I'm doing is collecting all the V weights over here. This is V1 plus dot, dot, dot. What's left is Vn AN. I've just separated all the U's from the V's in the weights here. And what I get in the end is, well, this should look familiar. This is just, by definition, this is just A times U. And this is A times V. Okay? So in the end, what we get is A times the product, or the sum of two vectors is just the sum of those two respective products. Okay? And I think I'll let you maybe think about B. It's a similar idea. If you go back to the definition of matrix multiplication as a certain linear combination, you'll see that the B holds. But again, these two properties we'll come back to in future lectures. One more time, the matrix multiplication in some sense preserves sums and it preserves scalings. That's kind of the way to think about these two properties. That's it for now. We'll see you next time.